Hi to everybody. So for today, I'll be giving the last lecture for the methods of proof. So among the proofs that we have already discussed, this is the, the method of proof that is quite different among the rest. And this is called the proof by mathematical induction. To begin with, let's define what's mathematical induction. So mathematical induction is a technique for proving a statement, and particularly the statement that is given comes in a form of a theorem. If not a theorem, then a formula. But the theorem and formula, or the theorem or formula that may be given in the problem is asserted about every natural number. So when we say natural number, the set of natural number is the set of all positive integers. Okay? All positive integers. In other words, the set of natural numbers is the set of our counting numbers. So we have 1, 2, 3, and so on. Okay? And then when we say that this is true for every natural number, then the word every, as we have seen in the past discussion, is a quantifier that will now refer to all natural numbers. Okay? So for the mathematical induction, the theorem or the formula that we will be given will involve the set of natural numbers. And the statement given must be true for all natural numbers. And how do we go about the proof? So one good thing about the proof by mathematical induction is that we have some steps to follow. So unlike for the previous methods of proof that we have discussed, sometimes you really have to guess what will be my next step, what will be needed in my proof so that I can go about the final conclusion that I need. Unlike those methods, we now have the steps for mathematical induction. We have 3 steps. So the first step is to show that the statement is true for the first value. So for the first value, okay? So what is important in the first step? We need to show, I have already highlighted that the statement is true, and this is now for the first value of whatever theorem or whatever statement is given. So whatever first natural number is needed in the theorem, that is what we will be using for step number 1. And then for step number 2, in the formula given, we will now assume. So we don't need to show anything in step 2, but we will make this as an assumption. We will now assume that uh, a value k in the theorem will be true. Okay? Then, after assuming that a value k is true for the theorem, the third step is we will now show that if we use k plus 1, this statement must be true. And if we now have shown step 3 to be true, we can conclude that the entire statement is indeed true. So why is that so? Because what we are saying here is, okay, for step 1, the first value is true, so it exists. And then step 2, we just assume that for a value k, the entire statement is true. And then we go to step 3, k plus 1. So why is that so? Remember that in our theorems, in our statements, we are considering the set of all natural numbers. So meaning we are considering an infinite set. So in step 2 and 3, we are now saying here that if the statement is true for any value k, and if it is also true, if we can also show that it is true for its succeeding value, then the statement will be true for any value of, of the natural number. Because we have shown that in any succeeding values, both are true. Let me show the steps through some examples to make things clear for you. Example number 1. By the way, the examples that I'll be solving here are some of the problems in your modules. I'm not doing the problems that were already solved in your modules. You can go through those examples again. At least you have additional examples, solve problems in your modules. But I have chosen some of the problems in the exercises that I have given there. So problem number 1. Show that we have 1 plus 3 plus 5 and so on until we have 2n minus 1 is equivalent to n squared. Okay, so what we are saying here is that if we choose a particular n, where n is a natural number, if we substitute n in the left side, if we add all the natural numbers that we get in the series, it is just equal to n squared. Okay, so for example, if your n here is, let's say, 4. So if n is 4, you have 2 times 4 is 8 minus 1 is 7. So it means if that will be 7, you will be considering 1 plus 3 is 4 plus 5 is 9 plus 7 plus 7 is 16. Okay, 16. Remember, your n is 4. 16, 4 squared is 16. 16 equals 16. So that is the meaning of our statement. But we want to show that this is true for all values of n. Of course, if we will just do proof by example, we will not be able to finish our proof because the set of natural numbers is infinite. We have infinitely many numbers that can be substituted as the value of n. That's why we now have to introduce our proof by mathematical induction. Okay, so going now to the proof. What is step 1? Step 1. Step 1 is, okay, if n is equal to 1. Since 1 is the first entry here, we now choose if n is equal to 1. So if n is equal to 1, we have 2 times 1 minus 1 is this equal to n is 1, 1 squared. So we're just substituting. 2 times 1 is 1, minus 1 is 1. So clearly, if n is 1, we get the first entry. And then we have 1 squared is 1. So that must be true. Step 1 is satisfied. Step 2, we now assume n equals k is true. N equals k is true. If n is equal to k is true, then we have 1 plus 3 plus 5 plus dot dot dot. We change n by k, so we have 2k minus 1 is equal to k squared. So again, in step 2, we will not solve anything. We will assume that the statement is true. Step 3. So what will be done in step 3? Step 3, we have to show. So show that n equals k plus 1 is also true. So we have to show this. We have to prove this. And if k now, or if n is equal to k plus 1, so we get 1 plus 3 plus 5. So this time, dot, 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 plus our n is k plus 1. So if our n is k plus 1, we change n by k plus 1. So we have 2 times n is k plus 1. Okay, so minus 1. So we just replace n equals k, and then the right side is n squared. N is k plus 1. So n is k plus 1. We now square this. So that's the question. Is the left side equal to the right side? Okay, so if you will notice here, I place a space here because what we will be doing is, let's just go back here. Remember that this is for n is equal to k plus 1. In the previous step, we have considered n is equal to k. So remember, k and k plus 1 are always numbers in the in the set of natural numbers. They are consecutive numbers in our set. So it means if this is for n equals k plus 1, the entry here is for n equals k. N equals k, and remember that if n is equal to k, we get 2k minus 1. So where did I get that? It came from this one. This is if n is equal to k, right? Then n equals k plus 1. This is n equals k plus 1. Okay, next. What can we notice here? You will notice that in this line, this is very important. In this line, this entire thing here is actually the value that we have here. Isn't it? They are exactly the same. Which means if they are exactly the same, then we can get this value as the representation of this entire sum. Therefore, 1 plus 3 plus 5 and so on until 2k minus 1 is equivalent to k squared. Okay? Equals k squared plus, we now copy this. Let me simplify this. This is 2k plus 2. Okay? That's 2k plus 2 minus 1. Or that will now be 2k plus 1 when simplified, right? That's 2k, 2 minus 1 is 1, so that's 2k plus 1. And then the right side is k plus 1, the quantity squared. So we want to show that they are equal. And look at the resulting expression. Isn't it that in the left side you have a trinomial, and this trinomial is actually a PST, perfect square trinomial, which can be factored as k plus 1, the quantity squared, right? Which is exactly the same as the right side. Okay, now, if you don't see this as a perfect square trinomial, what you can actually do, another way that you can do this is you can expand this. If you expand this, you have a binomial raised to 2, square the first term, that's k squared, plus get the product, k times 1 is k, times 2 is 2k. And then you square the second term, you have 1 squared is 1. You get k squared plus 2k plus 1 is the expansion of this. So the left side is equal to the right side. Better still, we have the factored form of this. This is a perfect square trinomial. So what's a perfect square trinomial? There are two perfect square terms. K squared is a perfect square. 1 is a perfect square because it's the same as 1 squared. Square root of k squared is k, square root of 1 is 1. So k times 1 times 2. The remaining term is twice the product of the square root of the two perfect squares. Those are the properties of a perfect square trinomial. So to factor this, we have k plus the square root of this, 1, the quantity. So we have proven that step 3 is true. So what will be our final conclusion? So final conclusion, therefore, 1 plus 3 plus 5 plus dot until we have 2n minus 1 is equal to n squared. So that's the first example for the proof by mathematical induction. Let's go to a second example. Again, this problem is in your module, one of the problems in the module. So we have to prove that 1 squared plus 2 squared plus 3 squared and so on until n squared is equal to n times n plus 1 times 2n minus 1, everything divided by 6, excuse me. N is the set of, or n is any natural number. So this must be true for all natural numbers. So we have 3 steps. Step 1, show that if n equals 1, this must be true. Okay, is this satisfied? So if n is 1, go back to the left side. If n is 1, here, n is 1, 1 squared, right side, n is 1. So we have 1 plus 1 plus 1. So we're just changing all the values of n by 1. So we have 2 times n is 1 plus 1. Everything divided by 6. So we have 1. 1 squared is 1. So is this equal to, this is 1. This is 1 plus 1 is 2. This is 2 times 1 is 2 plus 1 is 3. So 1 times 2 is 2 times 3 is 6. 6 divided by 6 is 1. So we have proven here that 1 is equal to 1. Okay? So this is already proven. 1 is equal to 1. Step 1 is done. Step 2. Step 2, we assume n equals k is true. So assume that n equals k is true. So we now have 1 squared plus 2 squared plus 3 squared and so on plus k plus k. Let me erase that. Let me just fix it. Plus k squared equals the right side. We change n by k. So every n that you find in the right side, you just change it by k. That's k times k plus 1 times 2k plus 1. Everything, we divide it by 6. So again, in step 2, you don't need to solve anything. You don't need to prove anything. You just assume. And step 3. In step 3, this is where we will be showing something. Show. So what will we show here? Show if n is equal to k plus 1. This must be true. Show that if n equals k plus 1, this must be true. So we go back again to our expression, change every n that you find by k plus 1. So you have 1 squared plus 2 squared plus 3 squared dot dot dot. So you have n is k plus 1, k plus 1, the quantity squared, and is this equal to our right side? We have n is k plus 1, k plus 1 multiplied by n is k plus 1. So that now becomes k plus 1 plus 1. Okay, we just substituted it here. Then the other term is 2 times k plus 1 plus 1. Okay, plus 1 still. Oops. So plus 1. Sorry for the space. Plus 1. Okay. Then everything divided by 6. So that's the third step. But before we proceed with the complete proof, let's just go back in this section. Remember, this is until n is k plus 1. So before k plus 1, you have k. Because if you get the series, you have 1 squared, 2 squared, 3 squared, and so on, plus k squared, plus k1, k plus 1 squared. So let's just include here plus k squared and then plus k plus 1 squared. Again, why am I intentionally writing that? I am intentionally writing that because, again, if you will be observant, this entire section here is seen in step 2. This is exactly the same with our expression here before k plus 1 squared, which means we can again substitute the right side for this section here. Therefore, we need another slide. So that is k plus 1 that's k times k plus 1 multiplied by 2k plus 1. 2k plus 1 2k plus 1 divided by 6 plus what's that? Here, k plus 1, the quantity squared. K plus 1 k plus 1 the quantity squared, and the right side, let's just check that. The right side is, I think we can simplify this. Let's first check what will be the simplified value of the right side. This is k plus 1, that's k plus 2, because you have k plus 1 plus 1, that's 2k plus 2, 2k plus 2 plus 1. So that must be 2k plus 3. So k plus 1, k plus 2, 2k plus 3. Let's go back here. k plus 1, k plus 2, 2k plus 3. Everything divided by 6. So we want to show that the left side is equal to the right side. Now let's observe. We need our algebra here. If you will observe in your right side, you have a single term. It's single term in the sense that you have a single numerator divided by a single denominator. While for the left side, you have here two terms, a fraction plus k plus 1, the quantity squared. So let's work with the left side. And what we can do in the left side is maybe we can combine them first. LCD 6, isn't it? Because the denominator of this is 1. 6 divided by 6 is 1. So we just copy the entire numerator, that's k, times k plus 1, multiplied by 2k plus 1. Plus 6 divided by 1 is 6, times the numerator, which is k plus 1, the quantity squared. Of course, the right side, we just copy it. We have k plus 1 times k plus 2 times 2k plus 3. Everything divided by 6. So the denominators are already exactly the same. So we don't touch the denominators anymore. But the numerator, what can we do? This is still a sum. This is a factored form. So what can we do? So we can imitate what we have for the right side. Look at this. K plus 1. K plus 1 is a common factor. K plus 1. K plus 1 is a common factor, which is also seen here. So why don't we factor out k plus 1? So if we will factor out k plus 1, that now leaves us k times 2k plus 1, because we have factored out k plus 1 from the first term, plus we have factored out k plus 1, that's k plus 1 squared, so there's one more k plus 1 left, 6 is also left there, so that's 6 times k plus 1. Then everything divided by 6, and we have the right side. Next, what can we do next? Why don't we expand this? So if we will expand this, this is 2k squared plus k plus this is 6k plus 6. Or in other words, that should now give us k plus 1 multiplied by, what do we have here? 2k squared plus k plus 6k is 7k plus, this is 6. Then everything divided by 6, right side. Okay, so what do we have in the right side again? Maybe we can tap it here, k plus 1, k plus 2, and then we have 2k plus 3, everything divided by 6. We're almost there, I guess. Look at this, k plus 1, k plus 1. This is a factored form, k plus 2, 2k plus 3. And look at this, we have a trinomial. Why don't we factor the trinomial? We have k plus 1 trinomial. So if we will factor the trial and error factors of 2k squared, we have 2k and k. Why don't we try those factors? We have plus 3 and then plus 2. And let's double check. Double check. Do we have the correct factors? Let's try to expand this. 2k squared. Check. 3 times 2. Check. 3k plus 4k is 7k. So we have the correct factors of this trinomial, which we have on the right side also. So we now divide this by 6, and this is now exactly the same as the right side, k plus 1, k plus 2, and then we have 2k plus 3. Everything divided by 6. So you can conclude, therefore, you can just go back. Go back to the problem. So the conclusion there will now be the final conclusion of our solution will be therefore 1 squared plus 2 squared plus 3 squared plus n squared equals n times n plus 1 times 2n plus 1 divided by 6. That will be the final conclusion. One more problem. We have example number 3. So given 5 plus 10 plus 15 plus plus 5n equals 5n times n plus 1 divided by 2. So let's let's go over this. But why is my pen missing now? There you go. Let's start. Step 1. So step 1. If n is 1. So if n is 1, you will find n here. We just substitute. That's 5 times 1 because n is 1. Is this equal to, substituting n equals 1 in the right side, 5 times 1 multiplied by 1 plus 1 divided by 2. 5 times 1 is 5. This is 5 times 1 is 5. 1 plus 1 is 2. 2 and 2 will cancel out. 5 equals 5. So that's step 1. Step 1 is easy. Step 2 is easier because this is just an assumption. We don't need to solve anything in step 2. So assume n equals k is true. And what is n equals k? We have 5 plus 10 plus 15 and so on plus 5 times k. N is k. We have 5 times k plus 1. Everything divided by 2. So that's step 2. Step 3. This is the more tedious step. We have to prove if n equals k plus 1 is true. So we have to show that this is true. So this will now be 5 plus 10 plus 15 plus plus 5k, that's for n equals k, plus 5 times n is k plus 1. And then the right side, we have 5k, n is k plus 1. So that's 5 times n multiplied by n is k plus 1 plus 1. Everything divided by 2. Okay, so this is n plus 1. We have it there, n plus 1. And what will happen next? Like what we have seen in the previous solutions, the section right before n equals k plus 1 is exactly the same with the previous step. Therefore, we can now have this as 5k, which is this value here. We'll just inject it for the entire thing here. That's 5k times k plus 1 divided by 2. And is this equal to the right side? Oh, sorry. Before we before we have that, I forgot uh, this section. So this is just what we have here. What we have here right now is this entire thing. I forgot this part. We have 5 plus 5 multiplied by k plus 1. And then the right side, let's simplify. That's 5 times k plus 1. And that's k plus 1. Or that's k plus 2. K plus 2 divided by 2. Okay, we need another slide there. So that's 5k times k plus 1 over 2. 5k times k plus 1. So we have 5k times k plus 1 all over 2 plus, what's that again? 5k times k plus 1 all over 2 plus 5 times k plus 1. 5 times k plus 1. That's 5 times k plus 1. And then the right side is 5k plus 1, k plus 2 over 2. 5k plus 1, k plus 2 over 2. We have again 5 times k plus 1 times k plus 2, everything divided by 2. Please forgive me, it's so difficult to write using this tablet. Now let's work with the left side. So this is 5k plus 1. Okay, please forgive my handwriting. So if we will combine this, again, why will we combine? Look at the right side. This is a single fraction. So let's combine. LCD here is 2. So this is just, we just copy the numerator. That's 5k times k plus 1 plus LCD here is 2. 2 divided by 1 is 2 times 5 is 10 times k plus 1. And this is equal to the right side. Next, what can we do? K plus 1 is a factor. 5 is a factor. K plus 1 is here. 5 is also a factor. So we can factor out 5 and k plus 1. And in doing so, what is left? We have factored out 5. We have factored out k plus 1. So we're just left with k plus. We have factored out 5. So we're left with 2. We have factored out k plus 1. So that will be left there divided by 2. And looking at the left side, you have 5 times k plus 1 times k plus 2 over 2, which is already exactly the same as the right side. Okay, and since that's already equal to the right side, then we're done with the proof. So your final conclusion will be, again, just write your final conclusion. Your final conclusion will be, therefore, so I'm just doing a shortcut, therefore, 5 plus 10 plus 15 plus 5n is equal to 5n times n plus 1 over 2. So we have the 3 examples for proof by mathematical induction. So we have again the important steps. So step 1, assume or show that for the first value, so normally the first value is n equals 1. It's true. Step 2, assume that if you take n equals k, the statement is true, then finally show that the statement is also true for n equals k plus 1. Okay, so I hope this is clear. There are still several examples, there are still several problems in your module. Please work on those examples. So I guess this will be the last lecture before the midterm exam. So God bless you as you prepare for your midterm exam. Please review very well. And I'll just give the announcement regarding the coverage of your exam in your Google Classroom. Again, stay safe, everybody. God bless you, and God be your strength as you do all your requirements. I know you have so many requirements, so please just be patient. Okay, see you around.